I'm a lecturer. I lecture at Western Sydney University. So I teach. I passionately love teaching, but I sort of enrich my teaching with research. And I research water, the environment, animals, really anything that takes my fancy. But it's generally around water. I'm interested in water and how we relate to water. I love water. I did as a kid. I was a water kid. I loved the beach. I loved jumping in rivers. I was the youngest of 5, so I was frequently told to go jump in the creek. Keen on swimming, and I sometimes go with school classes to rivers, and I tell them, I don't know if I grew up properly because I grew up playing in water, and now I get paid to do it. I just love it. Rivers, so it's that beautiful part of the Australian landscape. I worked one summer on a cotton farm. That changed me forever. I was 21, and to grow cotton in Australia, they use lots and lots of chemicals. And I lived on the cotton farm, and they hammered it with chemicals. And then afterwards, in the waterways, I would see dead fish floating. That was a changing point. And I came back from that. I was about halfway through my degree, and I thought, us humans, we're doing something bad to this planet. How can I help us be a bit more clever about this so we have less of an impact? So that really kicked it off for me. With my research now, I'm working on so many different things all at once. I'm fascinated by drinking water, what we drink. I'm fascinated by our rivers and how healthy they are, and if they've got fish and life in them. And it's a bit of a grotty topic perhaps, but I'm interested in where our waste goes, where our poo goes, and what that does to the environment. I've done lots of work on that too. All aspects of the water, and it just comes from a curiosity. And remember, in Australia, this is the driest inhabited continent, and we have a massive struggle with water here. Either we've got too much of it, or what we've got isn't good for what we do. And there's just so many different research possibilities to work on that, and also to teach my students. So where does my research come from? How do I frame it? Well, firstly, I'm working on lots of different things all at once. And so I work with a team, and I work with research students. So I can work on lots of projects all at once. But where does it come from? It comes from a curiosity. And part of it is you answer one question, and you might answer that, but a few other things will emerge. And it's kind of it's like to me like a game of football. You might, someone might run with the ball up, get tackled, then someone else grabs it. It's like each frame of research is like that to me. So I'm involved in lots and lots of different things at the moment, but one of them, for example, is the influence of concrete on water. We're urbanising this country. We've got lots of urban gutters and pipes and things like that. And I'm looking at the impact of that. And that just came out of a conversation, a curiosity, thought about it, and then, let's do something. Where did this come from, and where did I get the hypothesis? I can remember I worked at Sydney Water at the time as a professional scientist, and it came from talking to a technician colleague in the lab. And I had just been and sampled a big urban waterway that had concrete channel sides. It's like if you've ever seen the movie Grease. It's like the river that they drive up and down in their cars. It's devoid of any life except for concrete and water. And I'd just been and sampled something, and he said straight away, so it had high pH. And it did. I thought, well, how do you know that? And it just came from that conversation, and I then noticed whenever I went there, this little idea, high pH, how does he know? And little by little this grew until we thought, we've got to study this. This is really interesting. And we've discovered that concrete and water is a reactive mix, and it goes off within seconds. And it's actually degrading, and it releases calcium, carbonate, potassium. Massive, has a massive reaction. If you're in a concrete building right now and it's wet, it's degrading. But your engineers probably know what they're doing. So how did we go about testing this? Number one, we just sampled lots of waterways, and in fact we had data from a whole lot of waterways, and it was basically looking at the old data, and then we made this generalisation, all the ones that are concrete or that come from highly urbanised catchments, so lots of buildings, footpaths and pipes, they all had higher pH, higher salinity level. And when we had the data of the actual minerals, like the calcium or the bicarbonate or the potassium, so we looked at the data, then we did pilot studies. And this was not romantic stuff. I tell you how I did it. I got a bucket of water, put tap water in it, threw lumps of concrete in it, and put a data logging probe and plotted pH and conductivity overnight, and went off like a skyrocket. And I knew I was onto something, but it literally came from under my house. So then we had the pilot study. We looked at the historic data. We had our idea. We then read up the literature. We then did searches. This is so obvious. Someone must have done this before. So we did our searching, and we kept coming across this blank. So for me as a scientist, I start to get like a dry mouth. There's a data gap here. Yet we talk to people and they go, well, isn't that obvious? And we go, yeah, it is, but where's the data? And by the way, why do we keep building so much bloody concrete? Everything's concrete. What is this obsession with concrete? So we had our data, we looked in the literature, we had this gap. For that fraction of time, for a few months, I was working with the council. I convinced them to fund something. And I then found a client for the research, and they funded a project so that we could do this properly. Funding is essential for science. Not all science, you can do a lot of research on nearly nothing. And some of the great scientists over the eons have done that and continue to do that. Amateurs have done some brilliant stuff. But these days it tends to be fairly expensive in so many ways. So it wasn't massive, but it was in the thousands of dollars, and we got enough to actually do some research on this to get good, hard empirical data to prove it and beyond any doubt to model this. I think one of the most important tools here was how, firstly, we're going to accurately measure this. So we got good, solid, very robust scientific equipment. It's really low tech, and it was measuring salinity, electrical conductivity of water. It's pretty straightforward, and pH, calibrating it to make sure that your data is of sufficient quality. It's pretty simple technology, and then we did repeated measures. So basically we repeated it multiple times and did sampling over time so that we could look at a curve. So we basically ran an experiment and then introduced concrete to water and looked at the change, and we did it several times. Now, your most important part of this was good, accurate data, but recording it. So really basic stuff, but how you record your data is just so important. We were doing it both electronically, logging it, but we also wrote it down because I don't trust machines with data. So we wrote it down as well. And then to work out, is there a pattern in this? Did this almost straight away because we wanted to see if it worked. Graphed it, graph paper. It's basic, sort of numeracy and pattern analysis. And we ran water through a concrete pipe, and we rotated water, and it was basically rainwater from a water tank, and we circulated it side by side with a plastic pipe and looked at the difference. And we just graphed it straight away, and you could see it. But then basic statistics. The statistics was actually powerful and simple simple can be very powerful. So we did analysis of variance. So it was a comparison between water in the plastic pipe, water in the concrete pipe over time. And very quickly we could see that there was a strong, statistically significant trend in time. We did lots of different experiments. We also did other simple one, which is ultra powerful, which is a t-test, which is just a comparison of two different things, with and without. But the secret is lots of replication, and then are your results a result of chance, or is it a solid, robust trend? And we got that solid, robust trend. We modelled afterwards. So we did our basic analysis, but we then basically, to me, the modelling is just looking at those relationships and then making a generalisation or a prediction. And we would use that model to then look at water in the environment, basically urban water, with and without urban areas. And our model picked up that with all the hard surfaces, roofs, roads, footpaths and things, had much, much higher levels of pH, of salinity, of calcium and potassium. It fitted our model. So we developed an urban water signature, which is based on the byproducts of concrete breaking down in water. By the way, don't panic. It breaks down over about 50 years. It takes a long, long time. So what do we do once we've got our science done? Well, for me, it's really the big step is getting it peer reviewed and getting it published. So is it robust? Is it solid? How does it compare to the literature? We went through that, and for many people in science, that can be the end point. For me, I like to see my science that makes a difference. So we then shared that. We shared that with both through the media, but more importantly to me, we went to the industry. So the water industry is really big in Australia. So is the concrete industry. And how this is applied is often through urban water management. So we went to conferences and we shared our results with them. And that then started a discussion with the big decision makers that are planning these urban developments, the regulators. I even spoke about it in the Land and Environment Court. I wasn't charged with anything. I was just talking to them at their annual conference about this sort of thing. So it's talking about all the different people who use the scientific information, and for me that's like a 101. I do my research to make a difference. So a really important part is getting your science peer reviewed. So we can all do science and say whatever we want, but if it's shonky, dodgy, missing bits, you haven't done your work properly, it will get shot down. It'll get cut to pieces. And a great way, sometimes a really hurtful way of ensuring that it's good is you put it out for a peer review. So it's an absolutely fundamental cornerstone of science. So I submit it to an international journal. It will then be reviewed by peers in my field. The editor will make a decision who they are. It's completely anonymous. And because it's anonymous, they can say some very hurtful things. But that happens all the time. So, you might be at school and get very hurt from criticism from your teacher. I'm 35 years out of school and I still get criticism from my peers, and it is still a great way to learn. And once I'm over the hurtful comments, it actually makes my science stronger. And in most cases, it's just a way of perhaps explaining a little bit clearer in perhaps how I did my research or how discussing the results. And very, very occasionally, it is just not good enough. And that's a great way to learn, to make sure that you're better next time. But either way, this just makes sure that when we have scientific output, publish our research, that it's good stuff, that you get the green light and can share it with others. What advice would I give? I believe in backing the horse self-interest. Study something that you're interested in, something that you're curious about. I wouldn't necessarily be thinking about marks or study, but pick a topic that you're curious about. That's always driven my science. Read up on it, see what you can find, but then try and work out what's the gap. What could I achieve? It might be something quite well known, but it might not be well known in your area, or you might choose a different angle. So have a think about it. It's quite an opportunity. Also look at the resources you might have at your school. So what facilities do you have available? I remember in high school, I was really lucky to have a chemistry teacher once who allowed me to take some equipment, and I did a survey of creeks. I was in year 9. And I look back on that, and that was probably a really important experience. He let me take chemicals away, and I did a study of my local creeks. And that as a school project is so similar to what I do 40 plus years later. So look at what resources you are, look at what you're interested in, and see it as an opportunity. Talk to people, ask questions, and I'll tell you what, I get contacted by school kids. Don't be afraid to approach scientists in your area and ask them.